Thank you. Yeah, it's a pleasure to speak here, and I want to speak about so-called perfectoid spaces. And as I was recently made aware of, there's independent related work of Kedlaya and Liu on pretty similar stuff. But anyway, so let me fix a non-Archimedean field K of characteristic 0, complete with respect to an absolute value of rank 1. And such that the residue field is of characteristic P. Positive prime number. And looking at the Frobenius map on the elements of positive valuation, of course it's not defined there, but it's defined if you mod out P, if this map is surjective. So other people would maybe call this a deeply ramified field. Okay. So some examples of such fields are you get a join to QP or P power roots of P and complete. You could adjoin to QP or P power roots of unity and complete, or you could also consider CP.
The definition you gave, you could also just QP, right?
Oh, sorry, yes. Yeah, non-discretely. Sorry. Yeah, sorry. That's by definition what I wrote. K plus is the set of elements of norm at most one. Sorry. Okay. Okay, to sorry, yeah. Excuse me, sorry. Okay, now to such a field I associate a field I call K prime, which is a fraction field of the inverse limit over phi of K plus what P, which you can also regard, I mean this is really a ring. As a set, you can also write it as the inverse limit over K for respect to the P's power map. And it admits the map to K just by projection to the first coordinate, which I write as x prime, and K prime maps to bracket x prime, because it's sort of a Teichmüller lift in some sense. And I wanted to fix a little bit more, of course. So first I have also evaluation on K prime, which just is defined by setting the absolute value of x prime to be the absolute value of its lift. And let me also fix sort of a uniformizer in K prime, except it's not discretely valued. So I take some element with norm strictly smaller than 1, and I don't want it to be larger than the absolute value of P, smaller than the absolute value of P. And then we also get some sort of a uniformizer in K just by taking this Teichmüller lift. And in fact, it comes canonically equipped with a set of P power roots of it. Okay. And in this situation, we have the following theorem, which in some cases was first proven by Fontaine, Bonton, and Berger. And is in general then due to Gabba and Romero, which says that we have a canonical isomorphism between the absolute Gara groups of these two fields. Okay, and let me give you an idea of where this isomorphism comes from in the way I see it. The Gara group, of course, just encodes a set of finite étale covers of finite étale K-prime algebras. And one can show that this category is equivalent to the category of almost finite étale covers of its ring of integers. Almost finite étale K-prime plus algebras, where plus again has the same meaning, ring of integers. And I will say in a minute a word about what almost is supposed to mean. And then it's also equivalent to the category of almost finite étale K-prime plus mod pi prime algebras by some unique lifting theorem for almost finite étale covers over nilpotents. But K prime plus mod pi prime is in fact just the same as K plus mod pi. Which again you can see by this lifting of almost finite étale covers as a category of almost finite étale K plus algebras. And then finally you see again that this is the same as the category of finite étale K algebras. So somehow you shift between the two characteristics by sort of reducing mod p and then lifting in two different directions. And almost here means it has a precise definition, and roughly it means up to mk torsion, where mk is the maximal ideal of K plus, which of course has a strange property that its square is still equal to itself, which comes from the fact that the valuation on K is not discrete. And
the prime side is the same up to K prime.
Of course, on the prime side it's the same up to putting a prime everywhere. So in my talk, primes will always denote the characteristic p side, and stuff without primes on the characteristic 0 side. And the real work in this proof is really in showing this equivalence here, which says that if you take a finite étale algebra and take its normalization, then this is an almost finite étale algebra. In characteristic P, it's in fact not so difficult, just because Frobenius shows that it's, well, I will come back to that point later. Let me now make the following definition. The Perfectoid K algebra is a topological K algebra R, such that R plus, which now means a set of power-bounded elements, is open with respect to this topology, and it's periodically complete and separated. Complete and separated. And additionally, we require that the Frobenius induces an isomorphism of R plus it's surjective on R plus mod pi, but additionally, I require that its kernel is already generated by the piece root of this uniformizer, which is sort of the minimal possible. Okay, and yes?
What does it mean to be how bounded in just an
Yeah, sorry. Maybe I should start the, yeah, I'm sorry. I mean, think of a periodically complete and separated ring, and then invert P. That's how it should come about, sorry. I mean, such that there exists R plus a periodically complete and separated ring, and R is R plus invert P. Sorry. Which then has a base of topology given by the P to the n times this R plus, and then power bonded makes sense. So it's unique. I mean, yeah, this is induced topology. Yeah. Primes everywhere, so in characteristic P, and then this condition here is equivalent to R prime being perfect.
So just to check, you wanted to think about as kind of a Banach algebra?
Yes, as a Banach algebra, yes. Mm-hmm. So, yeah, maybe Banach algebra would be the better word, but yeah, okay, sorry. And the theorem, which I think of some kind of tilting, is that the category of perfectoid K algebras is in fact equivalent to the category of perfectoid K prime algebras. So it's quite surprising. A category of characteristic zero rings is equivalent to a category of characteristic P rings. And the functor is just what you expect. So you take the inverse limit over phi of R plus mod pi, and then invert pi prime. So for example, K maps to K prime, and any L over K finite extension maps to L prime, which is sort of the one you get here. Yeah. And also, I mean, if you go to the algebraic closure, same stays true. And maybe more interesting, you can consider such rings like an affine algebra, but you take p power roots of the uniformizer. And such a thing is sent to the same thing in characteristic P. Okay. And in fact, this theorem is not so difficult, but at least it's somewhat a surprising fact. Now the next step is to associate to such perfectoid rings spaces, and at least for now I need a certain finiteness assumption to do so. Well, I will not spell it out, but it's basically saying that you can reduce everything to the that you want to do to the case of real affine algebras, but it's satisfied in practice. And so to such a perfectoid ring R, associate a space which is the adic spectrum of this ring R in the sense of Huber. And it's a set of all equivalence classes of continuous valuations. We going from R into some value group, totally ordered Abelian group, union 0. And well, I follow Huber's notation here, so these are multiplicative, although they are called valuations. So in fact, they are absolute values, in fact. But anyway, so the topology is generated by rational subsets. U, which are given as a set of all V, such that the valuation of Vi, that most the valuation of G for all I, where here I choose some elements in G and R, such that the F's generate R.
You want the F's to generate R, or the F's together with G to generate R?
The F's. I think.
I mean, the normal definition of rational subspace has.
I think you can always add G, just, I mean, the one, I mean.
No, you can get rid of G.
Yeah. Okay, and then we define a sheaf, or first a pre-sheaf, by requiring that on U it's given as you take R and you allow convergent power series in these variables. And similarly, we can define a space X prime and a sheaf OX prime. And now I should recall that there is a map R prime to R, sending some function F prime to its Teichmüller lift, just because R prime is again Z0 vertically just the inverse limit over the piece power map of R. And this map induces a map X to X prime, sending a V to V prime, which is given by V prime evaluated at F prime. Just the canonical construction. Okay, and then what we can prove is that in fact this map from X to X prime is a homeomorphism. OX and OX prime are sheaves. And if you take rational subsets of X prime, then evaluating the structure sheaves at this U prime, you consider also as a subset of X, or X prime of U prime. Both of these are perfectoid. And they are tildes of each other. So, in fact, everything sheafifies, so to say, over the space. And from here, we can just define general perfectoid spaces by gluing. Okay. So next I want to talk about étale covers of perfectoid spaces. Okay, so the starting point is the following proposition, which also occurs in the book of Gabber and Ramiro, that if in characteristic P we have a finite cover of a perfectoid K algebra, K prime algebra. Then, in fact, on the integral level, the extension that you get is almost finite etal. Which is a more general case of the characteristic P theorem. When R prime was K prime, I already used this fact. Okay, and the idea is basically, I mean, this is not very mathematical what I say now, but first there exists some very large n such that in some sense R tilde prime plus over R prime plus is finite etal. I'll just write fat up to pi to the n torsion. But because phi is bijective, this implies that it's same as true already up to pi to the n mod over p torsion. Then you keep going, and in the end you get mk prime torsion. So that's roughly how the proof proceeds. And it's really not a very difficult proposition. And so the next, so what this proposition also implies is that this ring, this cover, R tilde prime, is again perfectoid. Hence, we can tilt the whole situation, and we get a finite etal cover. And one easily checks that on the integral level it will be almost finite etal, just because it's true on the tilted side. Okay, and now we can do this for spaces. So to any perfectoid space x over k with tilde x prime, we get a fully faithful functor from the category of all finite etal covers of x prime into the category of all finite etal covers of x. Okay, but now the theorem of Fontaine, Vintém, Berger, and in general by Gabber and Ramiro says that implies that it's locally an isomorphism, locally an equivalence. you apply the theorem to the completed residue fields of your space X. But now if it's fully faithful and locally in equivalence, then you can glue everything, and you see that it is an equivalence. Always. So this means that any finite étale cover of a perfectoid ring R comes in fact from tilting, and hence we have this almost finite étale property here. So what we get is the following. Let R be a perfectoid K algebra with this finiteness condition star, which probably is even unnecessary. So it might be that using some more stuff of Kedlaya, one can show that one can do without this finiteness assumption here. So then if you have any finite étale cover of R, then on the integral level it's already almost finite étale. Which gives an almost purity theorem in cases where we don't have semi-stable reduction to everything. So we have a very general almost purity theorem now. And also the proof is much simpler than the proof of faultings. So okay. And now what we can do with it, so we can, for example, introduce an étale side, X étale, for any perfectoid space X. And a corollary of what we have done is that the étale side of perfectoid space is equivalent to the étale topos of its tilt.
So far we have looked at finite étale only, so how do you get
In Paretic spaces, it's true that locally any étale map is a composite of an open embedding and a finite étale map. And so we can reduce everything to the finite étale case. So it's different than in the case of schemes somehow. And some very concrete application of this is that if you look at the Pn over k, take its associated rigid space, or also adic space, and its étale topos, and then they take the inverse limit over phi, where phi is a piece power map on coordinates. Then you can easily deduce from the theorem that it's equivalent to the étale topos of the rigid space associated to the Pn over k prime. So in some sense, the Pn over k prime can be seen as a pro-cover of the Pn over k. So the same works for toric varieties. And so I expect that it also works for ordinary abelian varieties. In which case it somehow explains why an abelian variety in characteristic P has too few covers of degree P, because those are the ones that are killed in this infinite tower, whereas all covers of degree L survive this tower. And another thing which makes some connection to automorphic forms is that if you consider the ordinary locus of the tubular neighborhood of the ordinary locus in the modular curve. And on it, you have a canonical map phi, which is given by divide by canonical subgroup. And so again, you take the étale topo as associated to these. Then what you get should be the ordinary locus, but now in characteristic P, so over this field. Or if you like, you can also ignore this because it doesn't make a difference for the étale topos. Okay. So let me now discuss the first application of all of this. Which is, I can prove some de Rham comparison isomorphisms. And I should say that there's related work of Andreatta and Iovita in the crystalline case. And also this is very much related to the work of Brinon. So first I have to introduce a new site, which I call the pro-étale site. And for this, I assume that, for simplicity, that everything is quasi-compact and quasi-separated. So quasi-separated means that the intersection of two quasi-compact sets is again quasi-compact. So let X be an adic space over K a periodic field, so it's change notation. So, of finite type. And you can think of this just as a rigid space, because there's an equivalence of categories between the quasi-separated adic spaces of finite type and the rigid spaces. And now the objects of the site I want to consider are formal filtered inverse limits of ui to x, which is étale. And additionally, I don't want to, that they are getting smaller and smaller, so I require that the map ui to uj is finite étale and surjective for large I. So as pro objects, yes. Okay. Then I introduce what an étale map is. U to V is étal if there exists a map u0 to v0 of u0 0 étal over x such that this comes just by pullback. And it's called pro-étal. Just the same definition. So if u is the inverse limit of ui to v of maps which are étal and such that they are finite étal surjective for large I. And a covering is just a map, a family of maps which are pro-étal, such that they cover in the topological sense. So, and maybe I should say that to any such u, which is pro-étal over x, you have a topological space which is just given by the inverse limit of the topological spaces associated to ui.
In the definition here of pro-étal, u and v are
Themselves objects of x pro-étal, yes. There is some sequence of ui to v étal such that u can be written as the inverse limit.
But the ui are pro-objects, the ui are the actual.
No, they are also pro-objects.
So you don't get all map of pro-object to be pro-étal?
No. I will give an example in a minute where it's clear why I don't want to do that.
So the statement that ui to uj being finite étal was a statement each of ui and uj is a pro system.
Yes. So finite étal surjective again means comes from finite étal surjective at the finite level. Okay. So now we have such sheaves, such as the sheaf I call ZP hat, which is the inverse limit of Z mod P to the NZ. And we also have a sheaf QP hat, which is ZP hat tensor Q, and so on. So let us look at the simplest case. So in this case, I want to take the case where x is just the point. Then I claim that as a category, x pro-étal is just the category of pro-finite sets with a continuous action of the absolute Gara group, where to u, you associated its set of k-bar hat points.
Can I clarify one thing on QE? I mean, right, finite étal subjective for one. So you mean finite étal and for large I and j it's subjective, yeah?
Well, everything for a large I and j.
So for small I and j the maps don't have to be anything?
Étal.
They just have to be étal.
I mean, yeah. Yes.
Okay, so the UI to uj, they're always étal, but
But up from some point on, you only take finite étal covers because you don't want to shrink them anymore.
yes.
So.
Okay.
And so what are covers? So a pro-étale map, it's an open continuous GK equivariant map. And the open comes from this condition that from some stage on it's finite étale. And surjective, that's the point. I mean, everything is finite here. And covers are just topological covers, of course. But again, by open, continuous GK equivariant maps. Okay, and now assume that M is a topological GK module. And then to it, we can associate a sheaf, which I call Fm, and define it on a set U to be just the continuous GK equivariant maps from this profinite set to M. And then this is a sheaf. And it would not be if we did not require that the maps are open. And we have that the continuous Galois cohomology of M is in fact the same as the cohomology calculated on the sheaf X pro étale with values in this abstract sheaf Fm. So somehow all the topologies now somewhere else. And maybe I should also say that the sheaf ZP hat is just the sheaf associated to ZP with its canonical topology. So somehow this topology comes naturally. Okay. So now let me come to the Pierre-de-Koch theory. So what we can do, we can define the rings of relative periods as sheaves on the side. We have sheaves of relative periods. On this pro-étale side. So for example, there's a sheaf which is called Biederam Nabla plus, and you just adopt the usual definition. So you take the inverse limit of, you take the width vectors of, I should also introduce the projection map from the pro-étale side to the étale side. Of course, there's this map, and then you can pull back the sheaf OX plus, which you have on the étale side, divide by P, takes the inverse limit over all Frobenius maps, invert P, and divide by kernel of theta to the n and takes the inverse limit. Here, theta is a map from this inverse limit to OX plus hat, where OX plus hat is the inverse limit of OX plus or P to the n. You have this done. What?
You didn't say what OX plus is.
OX plus, okay, yeah. OX plus is the set of all elements in OX. such that the variation of x is at most 1 for all v in U. Okay. Maybe I shouldn't call them x, maybe f. And there's a second sheaf which is interesting for the de Rham theory, which does not have this nabla, and it's given by, okay, now again a long formula. It's already wrong. Where before taking this, and now again divide by kernel of theta to the n, where theta of course extends to a map from this thing to OX plus z, to OX in fact.
So now the first term is v over star OX rather than v over star OX plus?
Yes, I mean I could also apply plus and then invert p or something.
Okay.
But, yeah. And now the important proposition is the following, where all this machinery of perfectoid spaces enters. So first is that on perfectoid spaces covering X, so affinoid I should say, we can explicitly describe all of these sheaves. So basically, the statement is that you don't have to worry that you have to sheafify. Everything can be just calculated as it is.
By affinoid perfectoid space?
Hmm?
What does it mean for it to be affinoid?
Well, I mean, those that I glue. I mean, the spar of a perfectoid ring. Yeah.
Oh.
I mean, I should make some additional restrictions here. I mean, I cannot yet do it for any, but for a basis for the topology, so it's enough for everything. The second is that we have a Poincare lemma involving these enormous sheaves. And I forgot to say that I should assume that X is smooth of dimension n. Sorry. And what is also interesting and important in applications is that one can in fact find out what the sections of this enormous sheaf B de Rham plus are on étale maps to X, which is encoded by taking nu lower star, and in fact it's just OX. So in some sense, on étale, for things which are étale over X, this sequence is just what you would think of as a Poincare sequence, but it's not exact. But after extending these sheaves to enormous sheaves on this pro-étale side, the sequence somehow becomes exact. Okay? And one immediate application is that you can compare the cohomology of this sheaf B de Rham nabla plus, which should be sort of constant local system maybe, is the same as the de Rham cohomology of calculated on this thing of this sheaf. I mean, that's just by taking the cohomology of this sequence there. And now what we would like to know is that, in fact, this is related to usual de Rham cohomology, and this is related to usual Étale cohomology. And there we have the following proposition, which uses the map mu, but somehow at the level of the algebraically closed field. And it says that taking R nu lower star of this enormous sheaf, and I leave out a plus here, which is a slightly different sheaf, is in fact just some sort of completed tensor product of, I mean, here you have the one for k and here you have the one for x. So after projecting to this Étale topology, it's just basically all x is left. And the corollary is that if x is algebraic, then we get that these enormous de Rham cohomology is in fact the same as usual de Rham cohomology of x tensored up to Fontaine's de Rham ring. And what we get a map from the Étale topology of xk bar with coefficients in QP. There is a map to the Étale cohomology of this pro-Étale thing in this enormous coefficient ring. And now this is isomorphic to the Rham cohomology. And then the usual tricks show that this has to be an isomorphism. And in fact, everything works in the relative setting. Of course, he has to tensor with de Rham here, but then, yeah. So everything works in the relative setting, and we get the following theorem. So we let A be a smooth affinoid algebra. S0 is the spectrum of A0. And F0 from x0 to S0 is a smooth projective scheme, or smooth proper. And then we can define what it means for smooth QP sheaf on x0 to be de Rham. P sheaf on x0. And to such a de Rham sheaf, you can associate a filtered OX0 module E with an integrable connection. I mean, E is just given by mu lower star of sort of L tensor over QP or something with de Rham plus de Rham. And then the theorem says that then also all push forwards of L are de Rham, and it's associated to the de Rham push forward of Yes. So this satisfies Griffith's transversality
That's
automatically.
the assumption.
It's automatic
Oh, it's all.
because the connection on Biederam satisfies Griffith's transversality. Well, yeah, that's because sometimes I also look at the associated rigid spaces where the knot is left out. But yeah, maybe I should have.
Should I ignore the knots, or are they?
You can ignore the knots. They are not.
They don't mean anything.
Ah, so yeah. Yeah, I mean, ignore the knots. Yeah, it's probably better. Sorry. Okay.
Cannot be smooth when you take a direct image, so what happens?
What?
You start above with something smooth, but when you take a direct image, why would it remain smooth?
Well, the map is smooth and proper. Right?
Smooth and proper.
Oh,
Yeah.
proper. Sorry.
Okay. Okay, and now in the last 3 minutes, I want to give a second application. Which is the following theorem. That X and T over K a periodic field be a smooth complete intersection in a proper toric variety. Then if you consider the L-adic homology, xk bar, with coefficients in QL, L not equal to P, then this satisfies the weight monodromy conjecture. Or is pure of weight I as in Karajan's talk. And the proof just consists in covering this toric variety in characteristic 0 by toric variety in characteristic P as I explained it, and then approximating this smooth complete intersection by smooth complete intersection in characteristic P. And so reduce it to the characteristic P case. That's it.